Okay, so this is chapter 7. Chapter 7, which is rotational motion. Rotational motion and gravitation. So the first, I believe, first 4 sections deal with rotational motion specifically, and then 7.5 deals with so-called gravitation. So that section, I think I will do separately, because it kind of is separate. I mean, it's still, when we talk about gravity, we're talking about large objects like planets and satellites, or things that orbit around planets and planets that orbit around stars, and etc. These things are moving with rotational motion, so of course this fits in this chapter, but still the math is a little bit different in that section, so I might treat it separately. So first we have 7.1, which is angular velocity and acceleration. So the first 2 sections, velocity and angular, are going to be introducing these basically like kinematics around rotating bodies, or kinematics for things that move in circles instead of moving linearly. 7.1 is going to introduce these concepts, and then 7.2 is going to look at them for constant angular acceleration, i.e. like the same kind of thing that we were looking at with kinematics, right? Kinematics require constant acceleration. So in 7.1 to 7.2, you're going to see pretty much like the analogs of kinematic stuff, acceleration, velocity, displacement. You're going to see analogs to those things for rotational motion. And an analog just means like a similar like case, a similar case, meaning like analogous. Anyways, so we have, where are we? Let's see. Okay, so let me give these things some names. We want to talk about angular displacement, which we're going to call delta. So there's that delta symbol coming up everywhere, right? Delta theta, so a change in angle measure. We're going to want to talk about angular velocity, which we're going to use the Greek letter omega, which looks like a W with its the upper legs like curled in. So that's called omega. That's a lowercase omega. And angular acceleration, alpha. Okay. So let's look at a picture for what these things are, or at least definitely for angular displacement. All right, so okay, let's consider some disk. Some disk here centered at the origin for convenience. And let's say it's spinning, let's say that it's spinning clockwise, no, let's say anti-clockwise or counterclockwise around the origin. So the origin there is O, and we've got some sort of line that is marking the initial position. We'll describe that with some initial angle theta, so theta sub I. And then let's say that this object rotates until we have some new angle, theta sub F, for theta, the final theta, right? So of course, delta theta then describes that angular displacement, the difference in the angles here, the difference in the angles. So it's not like a linear distance, right? It's a difference of angles. Okay. Okay, so this may seem pretty clear so far, maybe, but I want to make a little bit more of a point about this angular displacement. Every point on this disk along this reference line that I've drawn for theta 1, so this red dashed line here, every point along this line will travel, will have the same angular displacement as it travels to this new reference line. So for instance, let me blow this picture up a little bit. Whoops. Okay, so we have center and theta 1, and then theta f over here somewhere. So some point P traveling to some new point P prime, these points I should say these points P to P prime will have the same angular displacement as, and then I'll draw some new points. Now I'll just use the same color, like maybe this point Q to Q prime. Okay. So this angular distance or angular displacement is the same as this angular displacement, which seems very strange. And whoops, I didn't really mean to draw over that. If you're okay with that, then that's good. But if that kind of gives you pause, and you might stop and say, well, but the point P is like traveling a farther distance. If you were to lay these out, it would be a farther linear distance, right? Because the point P is further from the center. And maybe you have some intuition about spinning things and know that things are a little bit different for the point P than they are for the point Q. The closer you are to that center of the thing that's spinning, things act a little bit differently, right? So that's true, but we have to be really careful about setting the stage here for discussing these things, because it's subtle. So what I've written down here is the correct way to describe them. The relationship between any point on this reference line to this reference line, they have the same angular displacement. In 7.3, we will look at that issue of talking about what is the difference between, because there is a difference, but we have to, it's in a different context. So for now, we say any point really along from this reference line to this reference line has the same angular displacement. Okay, good. So let's say this point has rotated. We'll go back to this picture. This point, let's just say on the edge to make it easy. So it doesn't matter, so to make it easier, let's say that we've got some point on the edge of this disk going from here to here through some span of time. Okay, so it's covered some angular displacement over some time. Well, we're going to define, I guess I can write it here, angular velocity as the change in angular displacement over the change in time. It's just like regular velocity, right? V is equal to delta x over delta t, right? Well, it's not exactly the same, right? But it's at least analogous. Okay, so one of those important little facts is based off of what I said about this issue, about any points having the same angular displacement. Well, then that allows me to say, what does that allow me to say about the angular velocity then? Okay, I need to make sure I'm saying this correctly because this is subtle. Alright, so as the object rotates, any point on the disk is undergoing the same angular displacement, right? That's what I said here. And I made the point about them being on this reference line to this reference line, but even if I pick some point here and then, you know, it rotates through and it lands here, then those 2 points have the same angular displacement as any other point, right? If it's a rigid disk and I rotate it, then all of the points that make up the disk are all moving together, right? It's not like a wiggly jello disc or something that only the outside moves, right? Like a CD. Like if I spin it, then every point, in fact, let me see if I can find something. Okay, so I've got a circular object, a rigid circular object now that I'm going to rotate through this angle, this delta theta here, theta 1, or sorry, theta initial to theta final, and we'll see how for different points on this disk that they all have the same angular displacement. And the point of this is going to be, whoops, this needs to be more like that with the center, trying to line those up. There we go. The point of this will be that this is culminating in the idea that we can measure the angular velocity, not just of a single point of this object, but if you can get it for one point, then it's the same for all the points, and we say that it's the same for the entire object. So when we discuss angular velocity, we're going to say that it is, we'll say the angular velocity of the entire rigid object, not just points on it. Though sometimes we might have problems where we're just looking at a single point on the edge, maybe. So let's say if I rotate this through the angle theta 1 to theta f. So if I do that, I want to get this to rotate till those 3 points are lined up roughly there. Okay, there's that distance there. And now I'll put it back with those 3 points lined up there. And then if I pick some other point, just completely different, maybe much closer, here maybe, then if I rotate again, let's see, okay, here we go. Oh. Okay, a much smaller, I accidentally marked it a bit, but we'll say from there to there, a much smaller distance, maybe you might say, but still the same angular displacement. And then if I picked a point maybe all the way out here, and this time I'll go through, oh, come on. Ooh, this is difficult. Till those 3 points line up again right there. I'm lining up these 3 points. Okay, so the point is that for all of these are describing a rotation of delta theta, Out here, this is delta theta, here's delta theta right here, this is another delta theta. They're all the same. Now we know that they describe different lengths, different arc lengths, right? Because clearly this one is much longer than that one, right? But again, that's going to be the discussion for 7.3. Okay, so what do we have? Angular velocity of a rigid object, which is pretty much everything we'll be dealing with is a rigid object. Can be described by finding the angular velocity of any point on the object, and that is because they all have the same angular velocity at the same time. And again, omega, angular velocity, is equal to delta theta per delta t. And you can see that, like, mathematically, if you see back here what I wrote on all of these, if these are all the same delta theta, and presumably this displacement happened across the same amount of time, right? That's the underlying assumption here, is that these all happened under the same amount of time. Then you see if the delta theta is not changing, then omega is not changing. Again, understanding that delta t is being held, at some constant here. We're not messing with time here. So maybe I should be a little bit more technical here and say that this is the average angular velocity, right? You may recall, like, when we learned about velocity and acceleration, that we talked about average versus instantaneous. And there's similar things that are going to happen here. This is the average, and in just a second I'll describe the instantaneous velocity. But sort of in the same way that we kind of dropped that those technicalities in the kinematic stuff, and we just kind of assumed, we never really needed to write down whether velocity was average or instantaneous, because most of the time we were dealing with averages. Well, I should say either averages or just some velocity that we were asked to solve for, and we just called it velocity. And that it'll kind of be similar here. Okay. By the way, the unit of measurements is radians per second. Or per seconds. Per second. Okay, so let's go ahead and write down that instantaneous. How do they define it? So in the same way that instantaneous velocity, back when things were linear, was the velocity of an object as time shrinks to zero, right? So if you just pause time, how fast is the object going? It's a similar thing for instantaneous angular velocity, which they just call omega. So instantaneous angular velocity, omega, is the limit of the average velocity as time approaches zero. So it's omega is equal to the limit as, well, whoa, not time, as time, dang it, as change in time. Change, not just time tending to zero, I meant change in time, right? Like the difference in the time interval tends to zero. So we're taking a snapshot, like a picture of some moment in time. As that change in time tends to zero of the average velocity, average angular velocity, we get instantaneous angular velocity. So if I was to rotate this object and through some angle delta theta like this, and you took a snapshot of it, froze it at some point in the middle, so that delta t is tending to zero, so you're freezing time. so the change in time is now 0, then if you were able to measure that velocity, that would be the so-called instantaneous angular velocity. And we can measure it numerically by hand, literally like make a table of values and make time this delta t gets smaller and smaller, and you can find the angular velocity that way. But I don't remember us ever doing that much really with instantaneous velocity, because without calculus you do have to do it numerically, and that's just a nightmare. Nobody likes doing that. So I think I recall that we never really did that much with it in the linear case, so I'm presuming that we won't really use this much, to be honest. We might do maybe like one problem. I should say though that if velocity is constant, right, so here's a fact. If velocity is constant, well, if angular velocity is constant, then what can we say about average and instant? Oh, I keep leaving the word angular off. So used to just writing velocity. Instantaneous. So if we have some average, if the angular velocity is constant, like this, so it's never changing, and then you freeze time, what is the velocity at that time as you froze it? Well, it's just what it was the whole time. If it's constant, then the instantaneous angular velocity is just whatever the average, whatever that constant velocity is, it's all the same if it's constant. And that's not unique to this angular case. That was true back for linear stuff too. I don't remember if we pointed that out, because really honestly I don't think we even said that much about this at all. So maybe we didn't even point that out. Okay, and another analogous thing with this angular velocity is we call the speed, right? Recall speed was just magnitude of velocity, so we call the magnitude of angular velocity the angular speed. So it's just the angular velocity without its direction, right? Without its direction. Speaking of direction, we say angular velocity I have to define the positive versus negative, right? Like in a linear case, to the right was positive, to the left was negative. We say angular velocity is positive when the object rotates, that's just object rotates counterclockwise and is negative rotates clockwise. So that's the convention. Positive when it's rotating counterclockwise, and negative otherwise clockwise. Negative when it's rotating clockwise. That's the same convention you used in trigonometry, right? Angles going this way are positive, angles going this way are negative. So one last thing about the magnitude of the angular velocity, aka angular speed. So two things that are rotating with the same magnitude in different directions, like an object rotating at, 7 radians per second this way, has the same speed as an object rotating -7 radians per second this way, right? They have different direction but same magnitude. If the magnitude's the same, then the speed is the same. All these things should sound familiar. The concepts are sort of the same. It's just the terminology is changing. We're sticking the word angular onto the front of every definition here. And the definition of angular velocity itself is a little different. We had to think a little differently about the way an object moves, a rigid body object moves, right? With every point on here describing the same angular displacement. But besides that, things should be familiar. So I want to do this problem that they give in the text just to kind of get a feeling for how these definitions work, how these things are interplaying with one another so far. We haven't talked about acceleration yet. We will. So let's do this problem. And a lot of these problems are going to deal with, they're going to give you or ask for angular velocity in revolutions per minute, RPMs. So let's talk about that real quick before we dive into this problem. Okay, so revolutions per minute, also sometimes called RPMs, RPM, revolutions per minute, with the R being capital. Most of the time anyways, that's how I've usually seen it. So this really just boils down to a unit change, right? Some dimensional analysis, but it seems a little bit more important than that because of the connection between a full revolution and the number of radians. It really is just a unit conversion, but it seems to me to carry a little bit more weight, so I wanted to look at it in detail. So first of all, let me just say that one revolution, this is going to be the thing that gets us through the unit conversion, is equal to 2 pi radians. So this was terminology that was probably used in your trig class or either in trig tutoring maybe even when we describe a whole revolution as 2 pi. Technically, it's really 2 pi radians, right? And that idea from trig is gonna hold true here. And in fact, it literally has physical meaning now. A full revolution of a rigid body object, so taking it and rotating it all the way around, so from some point rotating it all the way around, one full revolution like that, describes an angle displacement of 2 pi. An angular displacement of 2 pi. So, well, I guess that's all I need to say here. It can get a little bit more complicated, I guess, if they describe fractional revolutions, like for instance a 1/4 revolution. Maybe they'll say something like 1/4 revolution, but really if we have the top equation here, then we can get to any kind of, we can do any kind of conversion we need. But may be helpful to just be able to recall, like a 1/4 revolution is pi on 2 radians. That's going from here right up to that positive axis. Half a revolution, like this, would be pi radians, etc. So it may be helpful to think about that for a moment, recall those those ideas from trigonometry. There's, of course, the issue of getting from minutes to seconds, but we'll have no problem doing that. Okay, so now for the problem. Okay, here it is. So problem 1 says the rotor on a helicopter, so the rotor is like the blades, on a helicopter turns at an angular velocity of 3.20 times 10 squared revolutions per minute. Part A says express this angular velocity in radians per second. Okay, so before we read the rest of it, let's just get this problem out of the way. The part A, it's the most straightforward, just unit conversion. So we want to take 3.20 times 10 squared, and I'm going to write it, instead of just RPM, I'm going to write it in a more useful form for dimensional analysis, revolutions per minute. And that kind of gives me a hint as to what I should do to cancel out the minutes and the revolutions. So I know that 1 revolution is equal to 2 pi radians from here, right? So recall that the way to do this is to say, okay, if I want to get rid of revolution, then that needs to be in the denominator since it's up in the top here. So I'll say times 2 pi radians per 1 revolution, and then getting rid of the minutes, 1 minute is 30 seconds. What? No, 60 seconds. I don't know where that came from. 60 seconds. 1 minute is 60 seconds. And just calculator work, right? So the units are canceling as we desire, and we're getting radians per second. So I'm just going to see what the book tells us this is, because I don't think we'll have a problem calculating that. We could write this 3.2 times 10 squared, by the way. We could write that as 320 if it makes you more comfortable. Okay, there it is though. There's the angular velocity. Now B says, let me see, I didn't write that quite clearly there. That's 2.00. It says if the rotor has a radius of 2.00 meters, so 2 meters, what arc length, so it says what arc length does the tip of the blade trace out in that many seconds? Okay, we want arc length. Arc length is one word. I accidentally put a space there. How do we get arc length? Well, maybe I should have written this down earlier, but I'll just quickly remind you now that arc length can be determined by, if you have an angle and a radius, then you can find arc length, and vice versa with the other relationships. If you have, radius and arc length, you can find the angle, etc., etc. So for some angle theta here, with some given radius, there is an arc length here, S. And the relationship is, or one of the relationships, right, is theta is equal to S over R. Okay. Out of order here. Okay. So we want arc length, that's the S. That's S. So manipulate this equation a little bit. We're getting R times theta. S is equal to R times theta. All right. But we have these. Oh, and moreover, I should say, if we're thinking about a delta theta, right, a change in angle, then what we have is some change in arc length. So I would say, now R is not changing. As the angle moves, as the point moves from like here to here, this is, or maybe from here to some new angle, we have some delta angle, right? Some difference in the angles and some difference in the arc lengths, but R is the same. So we would say delta S is equal to R times delta theta. So a changing angle results in a change in arc length, which makes sense. And vice versa, a changing arc length will result in a changing angle, but radius stays the same. Okay, so we want arc length. We need then delta theta and T. T we know, not T, what am I talking about? Goodness, we need delta theta and R, right, and R. We know R is 2 meters, but we don't know delta theta. Okay. We don't know delta theta. but we do know that omega is equal to delta theta per delta t, and that tells me that delta theta is equal to omega delta t. And they are asking for the arc length as the blade moves through this amount of time, 3 times 10 squared seconds. And I have the constant angular velocity, well, at least the average angular velocity. Did they say? They just, see, they don't even say angular. Did they? Maybe I didn't write it down. No, they didn't say. I think we're just to assume it's constant. For now, anyways. Okay, so we have an angular velocity, and we have some span of time. If you know how fast the object is moving, for how long, then you can find distance, right? Angular distance in this case. So we're getting that delta theta is equal to 33.5 radians per second times 3.00 times 10 squared seconds, coming from right there, right? And delta theta then is going to be equal to, and again, I'll just peek at the book to see what it gives. And we're keeping with the 3 significant figures, and we are getting 1.01 times 10 to the 4th radians. So this is a lot, right? This is spinning really fast, 33.5 radians per second. I mean, recall that a 1 radian is like roughly 60 degrees or so. It's yeah, really roughly 60 degrees. So this thing is spinning, you know, think about 2 pi is a full revolution. 2 pi is only like 6.28, and this thing is doing 33 radians. So it's spinning like roughly like 5 times per second, like completely around 5 times per second. So it's extremely fast. So in 300 seconds, it's spinning through a ton of radians. That's why this thing is times 10 to the 4th. This is like 10,000 radians. So this thing, well, it's a helicopter, you know, it moves, it's spinning extremely fast. Okay, so we're still not done with this problem, but we're almost there now because we have delta theta. So we want this arc length, delta s, is equal to r times delta theta, and that is giving us, from the given radius that was 2.00 meters, delta theta, which we just found, and we're getting, well, it would just be 2.02 times 10 to the 4th meters. Recall that when you, we say that radians they're like dimensionless. They're like a fake unit kind of thing. It gets a little weird there, but anytime you're multiplying these units together, the radians just kind of get swept under the rug. It's a little weird, but that's what happens. So this is the arc length that the blade, the tip of the blade, traces out in 300 seconds. That many meters, which is, what is that? 20. About 20,000. Wait, is it 20? Yeah, about 20,000 meters. So if you put a bug or something on the edge of one of the rotors on a helicopter and let it spin for 300 seconds, then that bug would travel an arc length of 20,000 meters. That's how fast these things spin. Now, this is getting into a little bit of that issue where things on the tip of the blade are going to cover more distance than things closer to the center of where it's spinning, right? So this arc length thing is going to come back up in later sections when we start talking about differences in speed at different points on the rotating object. But for now, for this problem, this is all they wanted, just the arc length. All right, part C is asking, let me come back, let me show what part C is asking. Part C is asking, the pilot opens the throttle, that just means he like steps on the gas, and the angular velocity of the blade increases. Okay, angular velocity increases, I'm thinking acceleration, but we haven't talked about that, so let's see what they ask. It increases while rotating 26 times in 3.6 seconds. Calculate the average angular velocity during that time. Okay, so they're not asking for acceleration, which is good because we haven't done that yet. We are instead looking for average angular velocity. Okay, well, I know that omega is equal to delta theta per delta t. So something to note is that, no, let me cover that up because that was from a previous answer. Something to note is that the problem is not saying that the velocity, that the blade spins 26 more times than it normally would have. It's just straight up telling us that in these 3.5 seconds or 3.6 seconds that it ends up rotating 26 times. And that is enough for us to find the average angular velocity, because this is what we'll do. We'll say, we'll get, when it says rotates 26 times, we can convert that to some number of radians, some delta theta. Right, rotates 26 times, that's just going to be 26 times 2 pi, right? Because one rotation is 2 pi, and it's doing that 26 times, so that's 52 pi. And how many seconds? Well, they straight up told us the number of seconds is 3.6. So that means omega here is going to be 52 pi over 3.6 radians. Over 3.6 seconds. I'll just say, okay. There we go. And then popping that into the calculator gives roughly 45 radians per second. Huh. Well, that's what the book says. What happened to them keeping 3 significant figures, I wonder? I guess, right. Anyways. So thinking about these things rotating and getting that to be some angular displacement is a very critical skill here. How many times did we do that? We did that in part A, needing to think about revolutions turning into radians, right? For this unit conversion for revolutions per minute to radians per second. We had to think about angular displacement a little bit differently here. This was just kind of, part B was kind of straight from the definition, right? If you've got angular velocity and you've got time, then you can find angular displacement. That's kind of just straight from definition here. But part C was back again to talking about number of rotations, getting from a rotation to radian measure. Because we always talk about angular velocity in terms of radians. So that's why we always have to get to radians. Instead of revolutions, we need to get to radian measure. Okay, so here's a question that the text poses. Okay, there we go. Saved me from writing it down. It says a rigid body is rotating counterclockwise about a fixed axis. Each of the following pairs of quantities represents an initial angular position and a final angular position. Okay, so A, B, and C here are just some theta 1, theta finals. That's all each of those are. Which of the sets can occur only if the rigid body rotates through more than pi radians, right? 180 degrees is pi radians. So which of the sets can occur only if the rigid body rotates through more than, well, let's look at the difference of these things. So theta final minus theta 1 for part A would be 3 radians, but pi is 3.14. So that's not quite 180 degrees. That's a little bit less, right? Because 3 radians is less than 3.14 blah, 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 blah radians, right? So that's not quite it's almost enough, right, but not quite. The difference between these is 2 radians. 1 minus -1 is 2. 2 radians is definitely not bigger than pi radians. Because again, pi radians is like 3.141592, whatever it is, right? So what about the last one? 5 minus 1, that's 4 radians. That's bigger than 180 degrees. So C would be the appropriate answer there. Suppose the change, let's look at this 7.2 here, right here. Suppose the change in angular position for each of the pairs occurred in 1 second. Which choice represents the lowest angular velocity, lowest average angular velocity? Well, if the time span is all the same, then we would want the one with the lowest angular displacement. So we would want part B, because that would be the lowest angular displacement. Is there anything, though, do we need to worry about which direction it's rotating? Well, no, they're all rotating, actually. They're all rotating counterclockwise from initial to final. Yeah, they go from small to big, small to big, small to big. So yeah, they're all rotating counterclockwise. So that's not an issue here. So yeah, you would just go for the smallest. The smallest one would have the lowest angular velocity because it's covering the least distance in the same amount of time. Maybe I shouldn't say distance, I should say angular velocity. Okay, so those are some good conceptual questions there. Okay, so now let's talk about changing angular velocity. When angular velocity changes, we have angular acceleration. Okay, just like the linear case. Changing velocity means some non-zero acceleration. The average acceleration, so alpha sub AV for average, is equal to delta omega per delta t. Or if you like to expand, omega final minus omega initial over, right? I didn't write this for any of the others, so, I mean, we know what the delta symbol means, but there it is, just in case. And the units is the radian per second squared. Just like meters per second squared, this time it's radians per second squared. And similarly to angular velocity, positive angular accelerations are in the counterclockwise direction, and negative are in the clockwise direction. But just like with linear acceleration, we have some weird relationships between acceleration and velocity, right? So let's look at these. So if acceleration, say, is positive, so this is counterclockwise, say counterclockwise, and omega is also positive, so going the same direction, then they are working together, right? They're working together. The object is speeding up. The rotation of the object is speeding up in the what direction? Counterclockwise direction. If alpha is positive in the counterclockwise direction, right, that's what alpha being positive means, counterclockwise, and omega is negative, so aka the clockwise direction, then the object is, what's it doing? Well, the acceleration is fighting the angular velocity. Slowing down. Now, what direction do I say it's? Well, it's currently rotating counterclockwise, but it's rotating counterclockwise and it's slowing down, and eventually it's going to slow down and then start spinning the other way. That's what the acceleration is going to do to the rotating object in this case. So, what should I say? The object is slowing down in the clockwise direction, because it's still going in the clockwise direction. Because velocity you can look at and know what's happening with velocity. It's either rotating counterclockwise or clockwise. You have to look at how the object is, its speed over time to determine what acceleration is doing. All right, so what if the case is that acceleration is counterclockwise and velocity is positive? No, dang it, sorry. Acceleration is clockwise and velocity is counterclockwise. So acceleration negative, velocity positive. Then again, they're fighting each other, so the object is slowing down. Anytime they're fighting each other, the object should be slowing down. So it's spinning counterclockwise, but acceleration is slowing it down, and then eventually it's going to go the other way. The object is slowing down in the counterclockwise direction. And then, of course, finally, we have speeding up in the clockwise direction, where they are working together in that negative clockwise direction. Okay. Similar to the way that instantaneous velocity, angular velocity were defined, we can have instantaneous angular acceleration. I'll just go ahead and write down the mathematical definition here. It's the limit. It's the same as all the others. You just send that time difference to 0 of the same definition that we used for average. You just send that limit as time difference tends to 0. That's it. All right. So they say what I said earlier here about angular velocity, but they say it for angular and they say it for velocity and acceleration, this bold-faced term here. When a rigid object rotates about a fixed axis, as does the bicycle wheel, so they were describing a bicycle wheel up above. What did they say? Every portion, I think they meant position. No, okay, yeah, that's fine. The way they said it is fine. Every portion of the object has the same angular velocity and the same angular acceleration. Good. That makes sense because as the object spins, all the points have the same angular displacement. If they have the same angular displacement, then they have the same angular velocity. If they all have the same angular velocity, then they must also have the same angular acceleration, because all these things are coming back to angular displacement, right? Angular displacement is the same, and the velocity is dependent on that angular displacement, so hence it's the same everywhere on this object. And then acceleration is dependent on angular velocity, so hence it's the same everywhere as well. Good. Now, what if we assume that the angular acceleration is constant? Well, then we will have this section, rotational motion, getting into this section. Well, what did we have? What was the big spectacular thing that we could do? When we had constant acceleration back in chapter whatever, 2, whatever it was. We had kinematic equations. Well, you know what we have for this section? Kinematic equations for rotational physical definitions. So I should say the condition is that, so the condition for the kinematic equations in the linear motion is that acceleration was constant. Fair, that's fine. In rotational motion, we have to say a little bit more. It has to have constant angular acceleration, of course, that makes sense, but we should also say it's about a fixed axis. So that's going to be the other condition. Now, I don't think we'll really be dealing with much stuff that's not on fixed axes, because that sounds scary. So let's just go ahead and say that these equations are for, let's write down these conditions that I've been describing. So rotational motion about a fixed axis with, let's say, alpha for angular acceleration being constant. And here they are. We have omega. Oh, okay, again, notation issues. I'm going to use final and initial because that just, I don't know, it just makes the most sense to me. Omega final is equal to omega initial plus alpha t. So of course you may recognize the analogous version. V final equals V initial plus AT. Then we have delta theta is equal to omega initial t plus 1/2 alpha t squared. That one looks familiar as well, I'm sure. And then the omega final squared equals omega initial squared plus 2 alpha delta theta. And then I think we had said we used a fourth one too, but it was just some combination of these. I don't really remember what it was. If it comes up, I'll write it down. But these are at least the ones the book writes down. So we're about to do a problem with these, but just to reiterate what's going on here is we're just describing angular motion. That's all it is. We're describing angular motion, and all of these weird terms, the angular velocity, angular acceleration, are just all coming back to some angular displacement, some movement from this point to this point with some angle in between. That's it. It's all just coming back to that delta theta, because all of these things are defined in terms of some delta theta divided by t or something like that, right? So it's just motion around a circle. Instead of motion in a straight line, it's motion around a circle. And all of the math, you could really get through this whole section, I think, at least these first two, without even really ever worrying about too much about what's going on physically, because the math all works out the same as kinematics does in chapter 2 or 3, whatever it was. So, anyways, let's do that problem. Where is it? Okay, so we have a wheel rotates with some constant angular acceleration of 3.50 radians per second squared. So that constant angular acceleration, that's the key phrase here that we're going to be using these kinematic equations. If the angular velocity of the wheel is 2 radians per second at time 0, so that's an initial, part A says through what angle does the wheel rotate, and then it gives us some time frame there. And it says give answer in radians and revolutions. Okay, so that'll just be a unit conversion. And then part B asks for some angular velocity at that time, and then part C asks a question about doubling. Anyways, we'll get to that. Okay, so part A is asking for, we want delta theta. Okay. I think we have some options here because we have omega initial to be 2 radians per second, because it's initial because it's at time 0, and we have, of course, the time span is going to be 2 seconds, and we have alpha. Actually, we don't have any options. We can only use the middle equation because we don't know that omega final yet. So we're going to use this equation. So let's send the equation this way. Delta theta is going to be 2.00 radians per second times 2 seconds plus 1/2 alpha 3.50 radians per second squared times 2 seconds squared. Okay, just plugging everything in there. That's going to be that's 4 radians plus that's going to be 2 times 7 radians. Okay. So delta theta is equal to 11 radians. Or, how many revolutions is that? Well, you would just say 11 radians times 1 revolution per 2 pi radians. So those radians will cancel. So that will give us, and I'm just going to peek at what the answer is, just to make this easier, 1.75 revolutions. So 11 radians or 1.75 revolutions. Any calculation we do in these kinematic equations, going to use radians. The revolutions thing is just an extra thing that the problem is asking for. Part B says find the angular velocity. So we want omega final. Because why is it omega final? Well, because I called this at time 0 that omega initial, and it's rotating from time 0 to time 2, and that's where I want the angular velocity at. So I'll use this as initial at time 0, and I'm looking for the final velocity at time 2 seconds. So I can use the omega final is equal to omega initial plus alpha t. So I'm getting omega final is equal to omega initial 2.00 radians per second plus 3.50 radians per second squared times how much time? Oh, 2 seconds. 2.00 seconds. Guess I could have just wrote 2, whatever. And I'm getting that omega final is equal to 2 plus 7, 9 radians per second. Nice. Nice clean use of these kinematic equations here. Now part C, what angular displacement in revolutions results while the angular velocity found in part B doubles? So this angular velocity found in part B doubles. Okay. So what they're telling us is that time has passed and the omega has gone from, after the 2 seconds, the omega has gone from 9 radians per second to 18 radians per second. Because they're saying what angular displacement happens while it's speeding up to 18 radians per second. So we want an angular displacement. We're going to set omega initial to be 9 radians per second, and then omega final to be double that. it's speeding up that much because of the acceleration, right? What equation relates all these things? Well, of course, it's the let's see, I'll write it here. Omega final squared is equal to omega initial squared plus 2 alpha delta theta. Can quickly reorganize this to be delta theta is equal to that difference in the squares of these two velocities over 2 alpha. And I did that because we're looking for delta theta, right? And again, the 9 to 18 came from the angular velocity doubling. So I'm going to have 18, I'm going to leave the units off here and just say 18 squared minus 9 squared over 2 times 3.5. And I'm getting, let's check the book for what this is because I can't do that one in my head. That's 34.7 radians, or, and again, converting from radians to revolutions in the same way that we did here, right here. So I'll just go ahead and say 5.52 revolutions. So ReV is fine for revolutions. Okay. So they ask a follow-up question here, which is good. It's another good thing to point out. Well, first of all, they say the result of part B could also be obtained from equation. Yeah. They're just saying there's another way to do that part B. That's fine. You may have thought about that too. You could find that final velocity first and then plug it into the other equation, whichever. There's, you know, with kinematics, there's always more than one way to do stuff. Question 7.2 says, suppose the radius of the wheel is doubled. Are the answers affected? Well, the answer is no, because angular displacement, angular velocity, and angular acceleration are not affected by where you are on the wheel, or the disk or the object. In other words, radius does not matter. For calculating arc length, radius very much matters, but not for angular displacement, velocity, acceleration. Exercise 7.2. I think this is just more kinematic stuff. Find the angle. Pause. Yeah, that was just some more small little follow-up calculation problems. I don't think they're really necessary. Okay. Okay, so next up is this 7.3 section, tangential velocity, tangential acceleration, and centripetal acceleration. So these things are having new names now, and you see that arc length is getting involved explicitly now, and we're going to have some new relationships for these velocities and such. This is where we're going to start talking about points having different speeds as they get further or closer to the center of the wheel or the disk or whatever it might be. And we'll have new names for those velocities and accelerations, and that's what the word tangential is describing there. So I thought I could do all of this in one video, but I need to let my voice rest and a little bit more time to prep for these, so I'm going to end this one here, and I'll do 7.3 and 7.4 probably, or maybe just 7.3 because it is a long section. I don't know. We'll see. We'll do the rest in the next video.